Okay, welcome to this afternoon's session. We're going to start with Sho Tanimoto, who's going to be telling us about sections of del Pezzo fibrations over P1.
Okay, so thank you for the introduction, and then thank you for the opportunity to give a talk here. So title is Sections of del Pezzo fibrations over P1. So, you know, so this conference is about the Fano varieties and so on. And the del Pezzo fibration, del Pezzo surface is the Fano surface. So two-dimensional Fano variety is the del Pezzo surface. And then, so del Pezzo fibration is kind of threefold fibered by del Pezzo surface over P1. So this is something I'm going to talk about. So one of the central objects in Diophantine geometry is del Pezzo surface defined by number fields. Del Pezzo surface over number field F. And then, so here, the del Pezzo surface means that, so X is a smooth projective, and the dimension of X is equal to 2, and the minus Kx anti-canonical class is ample. So it's Fano. So that's the del Pezzo surface. So most importantly, most famous example of the del Pezzo surface is the cubic surface inside a three-dimensional projective space. And then, so there are many questions about arithmetic of this surface. So, so first question is, can we decide when there's a rational point? So, can we decide when rational point exists or not? And then, so this leads to like you know, Brahmani obstructions, Brouwer-Manning obstruction, or weak approximation. This type of question we can ask, and there are a lot of study about these topics. And then on the other hand, also one another kind of famous topic is counting rational points. Counting rational points on X. And then there are many results about this, like an upper bound, and also like a Manning's conjecture. So ultimately, we like to prove Manning's conjecture for the del Pezzo surface. And then, so this is a very hard question. We even don't know any single example of a smooth cubic surface defined by a number field where we can prove Manning's conjecture at this moment. Right. So this is a kind of question arithmetic geometers are interested in, Diophantine geometers are interested in. And another interesting case. So today I like to think del Pezzo surface over different field. So another interesting case. So del Pezzo surface over C of t. T is a variable, and then so this is a function field over P1, and then so del Pezzo surface over P1. And then, so there are some bunch of results on this topic. So we can ask same question, when do you have rational points? Or, I mean, can we count rational? I mean, okay, counting rational point doesn't make sense, but we can make sense of something here. So for example, then famous result is by Graeber-Harris-Starr. So this is, you know, del Pezzo surface is rationally connected. In general, rationally connected, Fano variety is rationally connected. So, and then, so they prove that if we have rational connected variety over function fields, then there's rational points. Of course, this is just a Delpit surface, so you can prove this result without appealing to their theorem, where we can use classification of Delpit surface over ground fields, and then we can deduce this result without having using their result. But anyway, their also result implies there's a rational points. And also there are many results on weak approximation. So for some stupid reason, I mean, namely the Bra group for function field is trivial. Brahmani obstruction is trivial in this setting. So we can ask weak approximation, and there are many results on this topic. Okay. And then, all right. So then, so suppose we have a Delpit surface over function field, then one can think of a projective model over P1. Projective model. So then now let me define one notion in this talk. So suppose we have fibration over P1 is a Delpit surface is Delpit fibration. Delpit fibration if X is smooth, projective, and the dimension of X is equal to 3. So and then so pi is surjective with connected fiber with connected fibers. And then last condition. So we consider relative anti-canonical class. So this is just formally defined by minus kx plus pi star k p1. This is a relative anti-canonical class, and then this is a relatively ample. This is relatively ample. So in particular, by this definition, the general fiber is a smooth surface, and the anti-canonical class is ample. So this is the Delpit surface. So this is really Delpit fibration. Then I should make some remark about it. I mean, namely, so in general, suppose we have a Delpit surface over function field. Doesn't mean that you can construct a model with this property. In particular, problematic is smoothness. If we are some singularities, canonical singularities, then by taking relative anti-canonical class and using a minimal model, one can construct this model. But in general, I mean, that admits some singularity. So smooth one with this property, a smooth one with this property, we don't have in general. But anyway, so in this source, let me define this way. And then, so now we are interested in rational points on, sorry, I made a mistake. So rational points on X, right? So we are interested in rational points on X. And then, so then by variative criterion, this corresponds to sections on projective model. So this is space of sections. The space of sections. And then for each section, we can define height this is the height of C. So I'm assuming that, sorry, pi is Delpitz fibration right now. P1. So this is Delpitz. So this is Delpitz fibration, and the height of C is defined by intersection number with relative anti-canonical class. And then, so this leads to some sort of Manning's conjecture in this setting. So for example, like this height satisfies certain Northcott property, namely sections of bounded height are parameterized by finitely many families. So in some, of course, each family contains infinitely many sections. So you cannot get like finitely many sections. But you can say that there are only finitely many families parameterizing this section of bounded height. And then, so in this talk, Brian and I, we are interested in studying the following question. So classify components of a space of section. So that's the main question I like to consider. Oh, sorry. Okay. All right. So let me state first main theorem. So natural question. Okay. So first of all, one can ask to classify components of space of sections. But also, like one can first ask what's the dimensions of these components, and then we have a sort of answer for this question. So namely dimension of component. So main theorems. So theorem A. So this is the joint work with Lehmann and myself, and then we are still preparing preprint. It's almost there, but theorem is ready, but we are discussing examples, and discussing examples is kind of hard. So now suppose we have Delpitz fibration, Delpitz fibration. And then there exists some proper closed subset such that any component of space of sections parameterizing rising non-dominant family of sections parameterizes parameterizes sections in B. So in other words, if you have some section outside of B, then this is a member of dominant family. So you can deform section so that it covers the entire X. So that's what this says. And then why this is related to the dimension of components? Because for dominant component, we know that dimension is given by so-called expected dimension. So remark, for a dominant component, that means that it's parameterized dominant family of sections. Its dimension M is given by expected dimension, namely minus kx over p1 dot c plus 2 in this case, where now C is a member of M. And then for general C and for general C in M. So section defines some map from C to X. And then one can say that this map is free. So that means that the pullback of tangent bundle can be expressed like so in this case can be expressed like A0 plus or A1 plus or A2. Okay? I mean, so this is a vector bundle over P1, so you can decompose it into direct sum. And then free means that all, say, so these numbers are non-negative. So that's what free means. So in general, it's known that if you have like a dominant component, then general member is free. And if you have like a free curve, then dimension is given by expected dimension. This is general deformation theory of rational curves, space for rational curves. And then, I mean, I'm not going to give proof of this theorem. So in previous paper, we proved similar result for rational curves on Fano manifolds. So in general, for Fano manifold, if you have like smooth Fano variety, then, I mean, then we can prove that there exists some proper cross subset, and outside of this proper cross subset, rational curve deforms to cover entire X. And then this is actually proved using the invariant A in Marin's conjecture. So it's related to Marin's conjecture. And then, I mean, proof of this fact is similar, but it's involved more involved. But anyway, so essentially like we are using Marin's conjecture to prove this statement. Yeah, all right. So then, so today, I'd like to talk about bend and break. Mori's bend and break. So Mori is a birational geometer, one of the founders of a minimal model program, and then he got field mineral, and then he invented some technique about rational curves, and then we can improve his kind of technique in the setting of Pezzo fibration. So that's our main result. And then, so I'd like to talk about that. So then to do that, I need to talk about Mori's bend and break. So Mori's bend and break. So here we are going to explain some. So here, I think I'm going to state statement But the idea is the following. Suppose we have like a rational curve passing through 2 points. And then suppose that we can bend, like we can move rational curves while fixing these 2 points. Then eventually this breaks into like a union of rational curves. So that's the idea of bend and break. So let me state here. So suppose we have like a morphism from P1 to X, and then suppose we deform f P1 X while fixing 2 points. So that means that there exists some morphism from P1 cross another curve D. So D is a curve to X. Okay. So sorry, I made a mistake. So I don't need to be carry X, I guess, here. Such that D is a curve, smooth curve is a smooth curve. And then, so 2 points on P1 is mapped to 1 point. And map to x1, x2, respectively. So 0 is mapped to x1, no matter what d is, and then infinity is also mapped to x2, no matter what d is. So, and then also I need to assume that image of this surface is two-dimensional, is a surface. So image is a surface. Okay? Then Ft degenerates to a stable map. G from C to X, such that C is a tree of rational curves So it looks like, so tree means that there's no loop, okay? So tree of rational curve, and then C has at least two components, And then image contains both points, x1 and x2. So that's the Mori's bend and break. So idea is, suppose we have rational curve and then we move while fixing 2 points. Then it breaks into union rational curves. That's the bend and break. But there's an issue on this technique. One issue, there's no control on the number of components of C. You can have multiple components. There is no control of number of components of C. Okay, so that's the one issue. And then also, okay. And then also, even when F is free, component of C may not be free. So it's really difficult to control the bend and break. And then, so here's our main theorem we call movable bend and break. So theorem B, again, this is by Lehmann and myself in same paper. So we call like a movable bend and break. Right. So now suppose we have a derivative fibration. Del Pezzo fibration. And then there exists some constant depending on x. So we can explicitly compute this constant, and I'm going to give this formula for this. But anyway, so let me state the theorem. Some positive constant such that if m is a component parameterizing dominant family of sections, parameterizing dominant family of sections of height greater than or equal to this bound. And m bar, so now, sorry, I don't think I can explain here moduli space of stable maps, but essentially like a moduli space of stable maps contains also like a breaking, so essentially like this is a map from tree of rational curve to X. Yeah. So basically this gives us some kind of projective compactification of space of rational curves. So space of section as well. So I take the closure of this. This is the closure inside a moduli space stable maps. The closure of M in moduli space of stable maps. Then, so basically we can prove that M bar contains stable map whose domain consists of two components, so P1, P1, and each is free curve, free rational curve. So essentially what we can prove that curve break into the union of two rational curves, both are free. Then M bar contains a stable map. Stable map whose domain is P1, P1. So it looks like this. And then both bilaterally mapping to free curve. Both bilaterally mapping to a free curve. Okay, so that's the idea. And of course, now original curve is section. So result here, one is section, and another is vertical rational curve. So looks like this. So we have like a delta fibration like this, and then we have like this like a section, and then we deform, and then result is like a free section plus free vertical curve. So that's the movable bend and break. You can break into the free section plus free vertical curve. Yeah, so that's our main theorem. So first, let me explain one application of this theorem. So as a corollary, theorem B plus LT19. So this is our paper. My paper with Brian, which is published this year in Compositio. And then, so in this previous paper, so we kind of proved that Batyrev's conjecture follow from movable bend and break. And so we can conclude Batyrev's conjecture in this situation. So what's a Batyrev conjecture? So there exists some polynomial such that PD is an upper bound for number of components of space of sections. Parameterizing sections of height less than or equal to d. So I told you that so height satisfies certain Northcott property. So there are infinitely many families of parameterized sections of bounded height. And then we can prove that there's a polynomial upper bound for this value. So previously, like in Kora's book, there's some upper bound for number of components of Hilbert schemes and so on and so on. But these are exponential bounds. But actually, Batyrev conjecture that this should be like a polynomial upper bound. And then we can prove this polynomial upper bound in this setting. Using so essentially in previous paper we proved that assuming movable bend and break, we can prove Batyrev conjecture for rational curves. And then so now we establish a certain movable bend and break in this setting, so we can prove. So that's the one application. I'm going to explain. There are a bunch of applications of this theorem, so I will explain later. But then, so let me talk about some proofs. Though this theorem, proof of this theorem is kind of hard. It's really long. But two-dimensional case is kind of simple. So let me explain two-dimensional proof. So proof for two-dimensional, so surface, movable bend and break for surface. So that's not so difficult. So let me explain that. I saw that I'm going to give you the formula for Qx, but this is not so interesting and messy, so I skipped that. If you're interested in, please take a look at the paper. Well, it's not available yet, but once it's available. But anyway, it's really long formula, so it's not so interesting. So yeah, so let me discuss the proof when dimension is 2. How about when dimension of x is 2? So that's the, so I'm going to answer to that question. So let me define one value. So this is now minimum of minus. So let's look at all the section and then consider the minimum height. Okay? So I'm going to denote this number by like a neg. So by Northcott property, this is a kind of finite value. So this is well defined. All right. So then let me state theorem C, movable bend and break. Movable bend and break for surfaces. All right. So then this is generically P1 fibration. Generically P1 fibration. And then also, of course, I'm going to assume that Ly is smooth and projective and so on. I'm going to skip. Okay, let's write. Y is smooth projective. And this is the surface. And then she is a section such that height is greater than or equal to supremum of 2 and minus y over P1 plus 1. Okay, so that's the bound here. So Qx is more complicated than this, but I mean Qx also involved with this value. But actually it's involved more. But anyway, if we do this, then C is degenerated into section plus general fiber. So C0 movable section. And F is the general fiber. F general fiber. Right. Yeah. And then, so let me explain one lemma. I need this. So F singular fiber. So now I'm in the setting of theorem. So we have a surface. And suppose we have a singular fiber. So this is a tree of rational curve. Fiber. And then I'm going to assume, so I'm write F as union. So sum of components. So My is a positive. And then I'm going to assume that there are two components with multiplicity 1. Okay? There are two components with multiplicity 1. And then suppose Q to be another effective cycle supported on this singular fiber. And this satisfies Q dot Ej equal to 1 if I is equal to 1 minus 1 j equal to 1 if j equal to 2 and 0 otherwise. So suppose we have some effective cycle with this property, then one can prove that then minus ky dot q is positive. So I'm not going to explain this, but this is a kind of usual kind of blow up and so on. I mean this follow from number of blow ups and then induction, yeah. So induction on number of blow ups. But anyway, I'm not going to explain this lemma. This is easy. All right, so using this lemma, I can prove theorem C. So let me explain that. And then this kind of captures, this proof captures proof idea of the proof for theorem B. So you can feel what kind of idea I use in the proof. So proof of theorem C, right? So now I'm going to write height of C as n, and then by assumption this is greater than 2. Then under this assumption, using some usual standard deformation theory, one can prove that there exists one parameter family, of shear C passing through n general point, n general points. So this is true. And then, so now we fix more than 2 points. So we can apply bend and break. What I explained before. And then this break into some section plus union, some sum of general fiber, and then this is algebraic equivalent to one fiber. All algebraic fibers are algebraically equivalent to each other. General fibers are algebraically equivalent to each other, so I can write as one fiber, and then multiple. And then we have some curves supported on singular fiber. So C0. So this is now I'm applying bend and break. C0 is a section, so one can get section always, and the F a general fiber. F a general fiber, and then T does not contain a full fiber, and then end is supported on singular fiber. Supported on singular fibers. So I can get, by bend and break, Mori's bend and break, I can get something like this. And then, first of all, this is general fact of bend and break. You can conclude this from the proof of bend and break by Mori, that actually we can say something about result of bend and break. Namely, at least we can say that there are at least two components containing general points we fix. So this is possible to prove by looking at Mori's proof. So by B and B implies that there is at least two components containing general points. And then, so rational curve passing through general point is a free, so it's a movable curve. So this is general curve. So in particular, so T cannot contain general point. And then C0, we know that there are at least two components containing general point, and T cannot. So we can conclude that this implies that M must be greater than 1. So this is a guarantee by Bend and Break. And then, so fix a singular fiber, one singular fiber, F0, and let T0 be the sum of components of T contained in F0. So T can be expressed as like a sum of components in singular fibers. And then we only look at components contained in F0, one singular fiber. So then, this is kind of just intersection theory, elementary intersection theory. But by negativity lemma, if T0 is non-zero, this implies that T0 satisfies the assumption of lemma. So if you look at, so if T0 is non-zero, then one can prove that section C and C0 passing through different components like this. And then they must have a multiplicity 1 because its section passes through 1. And from that, one can conclude that T0 satisfies this assumption of lemma. The assumption of lemma. And then this implies that B equal to minus ky dot p1 dot t must be positive unless t equals to 0. Okay? So we can prove like this. And then our assumption, so, theorem C is gone. But anyway, so there's some inequality on height, right? Height is greater than like minus neg plus 1. And from that, one can conclude that our assumption implies that minus ky dot p over p1 c0 is non-negative. And then, so this is equal to n minus 2m minus b plus 1. I think, yeah, n minus 2m minus b. Yeah, right? Yeah. And then C0 can contain at most n minus 2m minus b plus 1 general points. And F, this is a fiber, so F can contain at most 1 general point. So breaking curve can contain at most this plus m points. But now remember that we fix first n general points, and then we break curve, we deform curve while deform curve passing through these n general points. So these number must be greater than or equal to 7, must be greater than or equal to m. And then this implies that only possibility is m is equal to 1, and then b is equal to 0. So, and then theorem is proved. So, I mean, this is kind of easy and cute, but I mean, you can prove like this using like some deformation theory arguments. All right. So then, last 10 minutes, I'm going to explain the application. So there are a bunch of applications. So applications. So let me give, so Movable Bend and Break can be proved, can be used to prove irreducibility of space of section applications. So let me explain that. Example. So suppose Y is cubic 3-4, smooth. And then I'm going to fix a pencil of hyperplane. And then let's denote X to be the blow up of pencil of a hyperplane. So pencil of a hyperplane contains, so I mean, two hyperplanes intersect along some elliptic curve. That's the base locus of pencil of a hyperplane. And we blow up. And then we are going to obtain some kind of a threefold. So this is the blow up of pencils. Well, of hyperplanes. Then it's clear that this guy is Pezzo fibration, is a Pezzo fibration, Pezzo fibration of a cubic surface of degree 3. Okay? And then, so you can compute many things. So first of all, we like to compute V in theorem A. So outside of this closed set V, we have like a section deformed to cover the entire X. So first of all, V in theorem A is expressional divisor of this blow up. Okay? So is E, where E is the expressional divisor of X over Y. And then I told you that this is blow up along elliptic curve. So expression divisor like a P1 fibration over elliptic curve. So only space of section inside E is just this, P1 fibration. So there's only one family inside E, one family of sections inside E. And then, so QX in theorem B is kind of large. something like a 5 or 6. So there's some formula, and I can compute using our formula. But actually, we can improve proof of theorem B. And then we can prove that we can improve the proof. We can improve a proof, our proof, and then show that actually 3 works equal to 3 works. So our proof is kind of constructive. So we can, we can analyze the proof, and then we can prove that equal to 3 works. And then also, I'm going to say that the minimum height is equal to -1, and it is given by sections in E. So they are the height, sections of minimum height. And then one can analyze irreducibility of space of sections for height equal to -1, 0, 1, 2 by hand. So one can analyze the irreducibility of, so this is a space of sections with height d. D for d is equal to -1, 0, and 1, and 2. Okay? And then now we can use Movable Bend and Break. So now, suppose we have a component. So suppose that d is greater than or equal to 3. So proof is a proof by induction. And take some component for a space of sections. And then since, there's only one family of sections inside E, automatically I can conclude that this is dominant component. Dominant. And then I'm going to take some space of vertical conics. Space of vertical conics. So each family, each fiber, derivative surface, there are finitely many family of conics, right? But then because of monodromy, so actually, so in this case, monodromy on Néron subject space on fiber is like a wide group. So it's maximal. So this is irreducible. Irreducible by monodromy. Irreducible by monodromy. So I can prove that monodromy of this derivative vibration is a maximum. And then from that we can conclude that this is irreducible. And then movable bend and break. Actually in this case we can improve movable bend and break. And then we can prove that we can break into section, free section, plus free conic. I can do that. So free section. And this is a free conic. And then this is containing section x over p1, d minus 2. And so if I denote like this, 1, this means that space with marked point. And then also here. So I can prove like this. So this is the glued component. And then using, so this is contained here, and bar. So this is contained here. And then using monodromy, I can also prove that this is irreducible. This glued component is irreducible. On the other hand, so using a deformation, so this is a free curve plus free curve. If you have a tree of rational curves, and if every component is free, then standard deformation theory tells us that this stable map is smooth point of moduli space. So I can prove that this stable map is containing smooth point of coarse moduli space. And then note that if point is containing two components, then it must be singular point of entire moduli space, right? So this means that there's a unique component containing this. So this implies that M bar must contain this guy. Because this guy is irreducible. So it must be unique. M must be unique. So by induction, this is irreducible and unique. So M must be unique. All right. So then that's another application, proving irreducibility of space of sections. Anyway, and then there are other applications. Other application, movable bend and break. I'm not going to write down, but let me state it. So first of all, Batyrev came up with a heuristic of Manin's conjecture for trivial family. But using movable bend and break, we can came up kind of improvement of Batyrev's heuristic for like a non-trivial family. So the general Delpit's vibration using movable bend and break. And then also like a stabilization of Arbery-Jacobi map. So if you have like a space of curves, then you can define, so this is threefold, so you can define Arbery-Jacobi map to intermediate Jacobians. And then they take the Stein factorization. Then we can prove that there are actually finally many Stein factorization coming from Arbery-Jacobi map when we vary like components. And then last thing is some enumerativity of some Gromov-Witte invariants of sections. All right, so I think I'm going to stop here. Thank you.
Thank you very much. Do we have any questions? Do you have any other examples for which you can prove that M is the unique component?
So
like intersections of two quadrics?
Compare section of two quadrics or like that. So if you have like 1/3 of index 2, then hyperplane sections, and you can construct it in the same way. So that's we handled it.
So for each of those, do you get a better bound for this constant Q?
Yeah, I think so. We did for degree. So for index 2, 1/3 increase degrees from 1 to 5, and I think we can do 3, 4, 5. But so 1, 2, so we have to handle degree 1 Delpit surface and degree 2 Delpit. That's kind of difficult. Like some argument like here doesn't work. So I mean degree 1, 2 Delpit surface. We have a movable bend and break, but we need some more specific result, and for that we need a degree to be greater than or equal to 3. So yeah.
Any further questions? Well, if not, we will begin again at 4 o'clock, but let's thank Sho again for a nice talk.
Thank you.